I'd like to start by thanking Saga Masui for this very nice invitation. It's an honor to actually open this meeting, your session this week. I'd like to start by making two remarks. First is I always like to know the audience I'm speaking to, so I can try to adjust the background depending on the number of puzzled faces I see before me. That's not possible today, so I apologize in case the talk is pitched at the wrong level. I hope it works out all right. And the second remark is that because this is a very general kind of talk, I have just added in the references at the end. I have not given any detailed references through the talk. So I'll show you those references at the end. Okay. So let me start. I'm going to talk mostly about our sun as advertised. And that leads us, since I'm a particle physicist with an interest in particles and their interactions, I'll talk about the particles called neutrinos and a particular peculiar feature of neutrinos called neutrino oscillations. That brings me to the India-based Neutrino Observatory, which I will spend less time on and the least or very brief amount of time on other stars, just for completeness. I see that there's another talk on astrophysics, so maybe you'll hear more about other stars in the other talk that comes up a couple of days later. So, how does the sun shine? I guess we all know the answer to this, but it's interesting to go back to the history and see that this was a question that was asked from von Helmholtz in 1854, who just talked about gravitational contraction of a large mass leading to energy emission, and after which Kelvin said, no, that's not sufficient, because if you have a chemical reaction that allows the sun to shine for 3,000 years, whereas if you have meteors which continually fall into the sun, then the energy of this will allow the sun to shine for 30 million years, and that seems like a more likely number. However, in contrast, a very unlikely player in this game, Charles Darwin, whom you would have read about in biology rather than in physics, said that no, the Earth must be at least 300 million years old in order to produce the observed erosion of the Great Weald of Southeast England. Actually, this is the first time I'm talking to, even though it's of course an e-talk, to people from maybe somebody from the Weald in Southeast England, which is what brought about this great puzzle, this contradiction between 30 million and 300 million years, because Darwin required this time scale for natural selection to produce the diversity of species that he found over there. Now, the sun's heat is responsible for life on Earth because photosynthesis is the primary source for all energy on Earth. So the sun must be at least as old as life on Earth. So you can see that the age of the Earth then and now, the origin of solar energy, and of course how long it lasts, very important questions for physics, astronomy, geology, biology, many sciences already, and it has continued to play a central role in today's work as well. So we know the true story. I guess all school students now learn this. It's nuclear fusion in the sun and in fact in other stars. Hydrogen fuses. And how does this happen? We go back to when the sun was formed. The matter in the universe was mostly hydrogen, and fluctuations of this uniform matter density cause small regions with higher density. Now, the most important thing is to understand that gravity is an attractive force. You know that electromagnetic interactions can be both attractive and repulsive, but gravity is very, very special. Gravity is an infinite range force, and it never turns off. That's what is the meaning of an infinite range force. It's a 1 by r squared force, but more importantly, it's always attractive. So the moment you have a fluctuation with a region which has higher density, then that just brings together higher gravitational attraction, and therefore more and more clumps are formed. And this continues until the compressed gas becomes hot. Its temperature and density increase to a point where the actual star is formed because the nuclear fusion processes start triggering off. And we know that the sun begins to shine due to the energy released by this fusion process. Of course, poor Kelvin didn't know about nuclear energy, so he missed his factors and orders of magnitude. But the primary source of this energy comes from transforming mass to energy, according to Einstein's very famous equation, E equals mc squared. And to understand this origin of this energy, we have to go back to the 1920 discovery by Aston, where he showed that 4 hydrogen nuclei are heavier than helium nucleus, which is very strange because the 2 neutrons inside the helium are actually heavier than the 2 equivalent protons, which form 4 protons. So the way to understand this is due to nuclear binding. Instead of single protons, when nucleons being both neutrons and protons, bind together into nuclei, just like how electrons and protons bind to form hydrogen atom, which has a lower energy than the 2 separate. In the same way, the helium becomes lighter than the hydrogen, And this mass difference, the mass equivalent energy, del mc squared, is converted into energy which is released when this fusion process occurs. So that is the origin of this energy, and this was understood only in the 1920s, about exactly 100 years ago. So it was Arthur Eddington who in 1920 said that hydrogen could burn for about 100 billion years in the sun. And just an interesting aside, I will not take this forward, but it's a very important question in nuclear energy. If indeed the subatomic energy in the stars is being freely used to maintain their great furnaces, it seems to bring a little nearer to fulfillment our dream of controlling this latent power for the well being of the human race or for its suicide. So very, very important words that he made in 1920 itself. But to go on with our own story, it took another nearly 20 years for von Weizsäcker and Hans Bethe to complete the calculation for how this fusion process of four protons converts into helium. And this is the amount of energy that it emits, which is seen as sunlight. And I will tell you a little about this energy unit in the next slide. So before I tell you about the energy units, something overlooked. So what was missing, you can see in the previous equation, was our friend, which is the topic of this talk, neutrinos. They are, in particular, you see the little subscript of E over there. These are called electron type neutrinos, and they are produced. I will tell you, of course, the whole talk is about neutrinos. I will tell you more about them as we go along. Uh, these new particles, I will just briefly tell you their properties. They were thought to be massless, but now we find that they are not. They're almost massless. They are completely charge neutral. And in particular, they hardly interact with matter, so they're extremely hard to find and to detect. Uh, okay, there's just a comment that very little energy of the sun is carried away by neutrinos. However, the number of neutrinos being produced is really huge. And you can check back and see that about 70 billion of these neutrinos are flooding the earth per unit area, per unit time on the earth. So if I put out my thumb through my thumbnail as I speak for every second, which is this, 70 billion neutrinos have passed through just coming from the sun. So the numbers are simply enormous. Okay, so let's get back to our story of nuclear fusion. Uh, this equation, which I've already shown before, I want you to look at each of these properties. So first of all, four positively charged protons, how do they even come together? So they have to be compressed close together, and this can happen because quantum mechanics allows their wave functions to overlap, so that these particles which normally repel each other are compressed because of gravity, and then Gamow calculated this probability of overlap in a quantum mechanical fashion. Once these come close together, and I will show you that it's not possible for all, rather very, very unlikely for all of them to come together at the same time, it happens in a series of steps. And in these series of steps, the net reaction is actually the following. And apart from this, a million electron volts of energy, and now I come to what is million electron volts. So here is the question. So Heisenberg, who has a very famous uncertainty principle, said that the smaller the object, so from atomic scales, which are 1 angstrom or 10 power minus 10 meters, to nuclear scales, which are 5 orders of magnitude smaller, Heisenberg's uncertainty principle tells you that the energy becomes 10 power 5 times larger if the distance becomes 10 power 5 times smaller. I'm sure many of you may have learned that the ionization energy of electron in hydrogen atom is 13.6 electron volts. If you call it 10 electron volts, then 10 power 5 times that is like millions of electron volts. And therefore, nuclear transmutations always involve millions of electron volts. In particular, this fusion process involves 26 million electron volts. So that is the first point. This much energy is emitted as sunlight. If you just stick your head out in the sun, you'll see that this much sunlight is falling on the earth pretty constantly over actually billions of years. Next, if you look at the orange line, it says baryon number conservation. There are four objects which sit inside the nucleus, which are called protons, which are types of baryons. And on the right-hand side, you have two protons and two neutrons, which are also called baryons. So this equation conserves baryon number. You can see that it conserves charge, okay? And in fact, the special new point is that along with the charged anti-electron or positron, which is required because there are four charged particles on the left-hand side, along with this electron type object, you needed to produce another electron type object, which is given the name lepton number. And therefore, these neutrinos occur along with these electrons to conserve something called lepton number. We will understand in a moment what that means. And of course, you always have energy momentum conservation. So I have introduced baryons, leptons, many names. So I want to actually step back for a moment and ask, what are all these objects? So in physics, you must have a theory for everything as much as possible so that you can write an equation and solve it, and then the rest is left to maths, right? That's how we proceed. So in particle physics in particular, to understand particles and their interactions, you have something called the quantum field theory. And the main paradigm of particle physics, which is the quantum field theory, I will show you by example. Any electromagnetic interaction, say between an electron and proton, whose physical consequence is to form an atom, is that these particles exchange a mediator particle, and here in this case it's the photon, and this mediation causes the interaction to be observed between the electron and proton. So all interactions are mediated by the exchange of mediator particles. And in particular, I want to highlight that everyone understands gravity because it's one of the most common, well-known forces. You all understand electromagnetic interactions, which we now know are mediated by photons. We know strong interactions because we know that's what holds the nucleus together. And finally, we have the new interaction, which is the weak interaction, where every particle in this universe experiences weak interactions, at least within the standard model. A very common example is radioactivity. And we will see that of all the interactions that are present, I'm not going to consider gravity here for various reasons, but you can see in the last line of this table that the neutrino experiences only weak interactions. And that's why, because weak interactions are weak, that's why they're called weak. It's very difficult to observe these particles. And also you can understand now that depending on these interactions, various quantum numbers are conserved. So this is the little background that I have given for particle physics. I'm sorry, everything comes in little packages because that's all the time I have. But I also want to highlight that therefore this neutrino and its partner electron are therefore called leptons. And in addition, there's a very peculiar feature of them that they come in 3 flavors or 3 generations. Just like you have an electron, you have a heavier version of an electron called the mu, even heavier version called the tau, and each one has its own neutrino. So nu e, nu mu, and nu tau are the partners of these 3 charged leptons, charged particles. All are negatively charged, their antiparticles are positively charged. And in fact, we don't even know if there are more generations and why they all exist. But within what we know, within the standard model, all these neutrinos were assumed to be massless. And in fact, this particular nu E is what is predicted to occur in the fusion processes in the sun. Okay, so now that we understand all these particles and the terminology, does the sun really shine in neutrinos? And the answer to this question goes back to understanding the fact that to observe these neutrinos, you must understand how this PP cycle goes. And I just want to highlight, for example, that there's protons, there's deuteron, there's helium-3, there's beryllium, boron, and you can see the red neutrino emitted at various parts of the process. And the energy, I'm sure you can't read this, goes from about 0.1 to about 17 million electron volts. So there's an energy spectrum, and different experiments will be sensitive to different energies. And of course, the proof of the pudding is actually to find these neutrinos. Then you can actually guarantee that the sun, which is so far away, is actually shining through this fusion process. Now, I've already said that they are hard to detect, but after many years, almost 30 years of working, the first experiments of Davis, who got the Nobel Prize for this experiment, which I will show you, actually observed the neutrinos from the sun. And what did he do actually? He took a very common substance, but he took an enormous amount of it. He took dry cleaning fluid, which contains basically chlorine 37, and this neutrino comes from the sun and converts the chlorine to argon. And you can see this very colored object here. The light blues show you that they are all leptons, but the neutral lepton is becoming a charged lepton. And in the chlorine, when the neutron becomes a proton, the chlorine gets converted to an argon. So you see argon and electron in the final state. And since these particles change the charge during the interaction, they are called charged current interactions. So this is the experiment that he did. He just waited with huge amount of dry cleaning fluid, and he gets about 1 event every 3 days. But what happens is that he found that the number of events observed to the number expected, if you look at the solar model, is actually about 1/3. So there are neutrinos from the sun, but they are too few. And an important criticism of his experiment was there's no guarantee these neutrinos were actually from the sun. So, are they solar neutrinos? This was actually addressed by the next person who got the Nobel Prize, Koshiba, and later on his collaborators. And they looked at a different, a beautiful experiment called the Kamioka 2, which was then upgraded to Super Kamiokande, which is still running. And they looked at elastic scattering in water, in very, very pure water, which is observed by thousands and thousands of photomultiplier tubes. And this is the experiment. It just kicks the electron in the forward direction. And so you can see that the events that they see are very flat, and where cos theta is 1, that is in the direction from the instantaneous position of the sun, there is a peak, which means these are actually solar neutrinos. So it's a brilliant experiment. Therefore, the sun does shine through fusion. There are neutrinos coming from the sun. Unfortunately, the ratio of observed to expected events was still less than a half. And what could be the reason for the shortfall? It turns out to be not solar physics, but some peculiar properties of the neutrinos themselves. And this is what is called neutrino oscillations. So to explain neutrino oscillations, I will go into a very simple two-flavor model. I'm going to forget the nu tau for now, and I'm going to assume that you know the elements of quantum mechanics. I can always write one state in terms of an overlap or a sum of two other eigenstates, nu1 and nu2, so that I have coefficients which are cos theta and sin theta, so that the probability of finding the neutrino still remains 1, because cos squared theta plus sin squared theta equal to 1. Since nu e and nu mu are orthogonal states, then the amount of nu1 and nu2 in nu mu is simply the orthogonal component minus sin theta and cos theta. So that means nu e and nu mu are not having well-defined masses m1 and m2. Nu1 and nu2 have the well-defined masses. Nu e and nu mu are produced in the interactions. And this is what is called flavor mixing. So what happens is that if I produce initially a certain combination of nu1 and nu2, which is nu e, as they propagate along in time or distance, because they're all relativistic, what happens is that since the energies or the masses of these two are different, they start to separate out. And at this time, you can see that essentially it's only nu2 which is going to be observed. If you put a detector here, at this time only nu1 will be observed. Okay, and this flavor mixing and the fact that the two masses are different causes you to have neutrino oscillation between flavors. And therefore, what you observe on the Earth is different from what is produced on the sun. And therefore, the statement is that the depletion of the solar neutrino flux is due to these flavor oscillations. Okay, so an obvious test is to look and see that if the nu e is depleted, that is because it is oscillating into nu mu and of course also nu tau. And a very beautiful experiment, which I have no time to describe, actually observed these other flavors. So we know now for sure that the neutrinos from the sun are exactly as required. The sun shines exactly as expected, but in the process, we have discovered some very peculiar properties of these neutrinos. And how do you know that it's due to oscillations and not anything else is something for you to ponder about and read about. I'm not going to answer it here because it's too complex to take up at this point. So what do we have now? We have assumed in the two flavor model that we have mixing between the two states, nu e and nu mu, so that it's possible that they keep oscillating into each other. And depending on where you place the detector, you will not see the total amount of nu e, but you can see different amounts of it. If you now extend this to the total three flavors in this very messy looking set of slides that you can see, I've written here what is current knowledge about these particles. So just like I had M1 and M2 in the two flavor example, when I include nu e, nu mu, and nu tau, I will have M1, M2, and M3. And then we know now that the oscillation experiments do not give the absolute masses of these particles. So we don't know where is the zero of these masses, but we know their mass square differences. And we know that this mass square difference, which is probed by solar experiments, is smaller than this, which is probed by atmospheric experiments, which I will talk about a little later. But whatever it may be, these mass square differences are really, really small. Moreover, we do not know the mass ordering. What do you mean by mass ordering? We do not know whether M3 squared is the most massive or the lightest eigenstate. So it could either be here or it could be here. This is known as the neutrino mass ordering, sometimes called the mass hierarchy, and it's an important input to understanding the theory of these neutrino oscillations. Of course, you can see the colors over here. The colors in this tell you how much is the mixture. So M1 squared is mostly nu E and a little bit of nu mu and nu tau and so on. That's what the colors indicate. And these are represented by, instead of one theta mixing angle, there are three angles which show you the mixing between the 1, 2, the 2, 3, and the cross generation 1, 3 mixing angles. So there's a lot of stuff going on in here, but this has been validated in many, many different kinds of experiments with neutrinos. And I want to highlight only one of them, that there is some interesting quantity called CP violation possible because there is another parameter called delta CP. And what does this do? It tells you that there is a difference of the interaction of neutrino with matter versus anti-neutrino with matter. And why does this happen? Because of this non-zero value of the CP phase, and that can be probed only if this angle is different from zero, and we see it's small but different from zero. And why do we want to probe it? If you look around at our universe, people talk about having seen galaxies all the way to very, very far distances, but nobody has seen anti-galaxies, right? If the universe began in a big bang, you would expect to see equal number of galaxies and anti-galaxies. But I do not see antimatter galaxies anywhere in the universe. That means somewhere either the Big Bang theory is wrong, or somewhere in the evolution of the universe, the level of interaction between neutrinos and antineutrinos or their properties are slightly different, so that all the antimatter in the universe naturally has evolved away and you're left with a matter dominated universe. So you, one possible origin, therefore, of this matter antimatter asymmetry arises from understanding neutrino oscillations and neutrino mixing, and therefore neutrinos are very interesting for cosmologists and astrophysicists because they hold the key to understanding the nature and evolution of our universe. Now, apart from that, as I said, one of the main quantities which is not known is the ordering of the 2-3 mass square differences. Okay, let me pause at this point. I can see many hands being raised. Is it that they can ask the uh, okay, let me see. Maybe I'll just pause, because in case there's a question on that slide. Okay. Okay, I'll just answer one of them. Andrew asked the question, do the charged leptons also undergo flavor mixing to some degree? Well, physics is a life of phenomenology, which means you must answer the observable universe. And in the observable universe, till today, no one has seen mixing between charged leptons. It's a very nice question. So as long as you don't see that, then you assume that electron, mu, tau don't mix. And in the particular mass, in the eigenstate basis in which these charged lepton masses are diagonal, which means they don't mix, you describe the mixing of the neutrinos in that same mass basis. I hope I have not confused people by that answer. I think the others are quite general, so I'll take them up later. I will proceed with my talk. Uh, so as I said, the mass square differences are really small and the ordering is not known, and this India-based neutrino observatory is being built actually to address this issue. So let me now just make a quick brief uh, uh, diversion into this proposed project. It is a proposed project. It's been funded but not yet started. It is a proposal at present, and it studies, in fact, atmospheric neutrinos. So cosmic ray particles from all over the universe interact with Earth's atmosphere and eventually produce neutrinos. These are called atmospheric neutrinos. And the primary neutrinos, both nu mu and nu e, and their antiparticles, which is not present in the sun, okay, almost equal in number, and nu mu to nu e in 2:1 ratio. We are really going to focus in INO on the nu mu type of neutrinos, and this detector called iCal detector is a magnetized ion calorimeter detector. It has 151 layers of iron interspersed with some active detector, and these orange things sticking out are actually coils through which current can be passed so that you can magnetize these detectors. So you look at this interaction in the same charge current interaction that I talked about in Davis's experiment. Instead of nu e producing an electron, nu mu produces a muon, and the anti-nu mu produces its antipartner mu plus. And you know that mu minus and mu plus have different tracks in a magnetic field. They will bend in different directions. So from the magnetic field information, I will be able to tell you whether the particle was a mu minus or mu plus, and hence whether the originating neutrino was a nu mu or a nu mu bar. Now there's atmosphere all around us, and the particles coming from above go through very short distances. The particles coming from below go through practically the entire Earth diameter, and in doing so interact with the Earth matter. There's no Earth antimatter, and that little difference in these interactions can be highlighted, and that can be actually used to probe the neutrino mass hierarchy. So that is the main content of this experiment. And this is, as I said, a proposal, and there's a lot of work going on because it's a very massive experiment. The magnetic field is going to be 1.5 Tesla, and it will involve these active detectors, which are 30,000 in number, and almost 4 million channels of electronic readout. It's a completely indigenous experiment, and this is a lot of R&D going on, so much electronics, so much of the RPC detectors, and this is a prototype that is now running and taking data for the last 2 years. Lots of students involved, a lot of excitement. So uh, coming back to one statement I do want to make about mass hierarchy, although the ICAL experiment at IONO wants to detect the mass hierarchy, apart from IONO, you can see an entire list of experiments: MINOS, T2K, NOVA, Pingu, Ice Cube, Juno, Dune, Hyper K, LB, all will or are probing the mass hierarchy. If you can kind of get back the slide and look at all these experiments, you will see the really innovative and fascinating ways in which each of these amazing experiments is trying to access and study the neutrino oscillation parameters. It tells you how much interest there is in the in neutrino physics, and it also tells you that, of course, these experiments are complementary but all competing with each other. But there's an amazing worldwide effort to study neutrino physics. That is the kind of interest in it. I want to make one remark with respect to ICAL. Most of these experiments will have to disentangle the effects of that CP phase, which I already mentioned, delta CP phase, from this hierarchy measurement. But the ICAL experiment can accomplish this independent of the CP phase. That is the USP of ICAL. And just to highlight, since I belong to that collaboration, I would like to say something nice about it. That's my nice statement about it. But the bottom line is that there are a lot of exciting possibilities in neutrino physics. Okay, so what we have learned now is that the sun shines through nuclear fusion. We understood how this nuclear fusion processes work, and it requires the presence of the neutrino. And then when we started testing this hypothesis, we got confused about whether the solar hypothesis was right, because the neutrinos didn't behave exactly the way that we expected them to behave, because there's not even the consistency between the two experiments. One saw uh, one third of the expected rate, the other saw half of the expected rate. And so, it was not even possible to put an overall normalization factor and say that, these experiments are okay to within a factor of something. But then we understood that it's not the sun, but it's the neutrinos which behave in a funny fashion. They're exotic. First of all, they have non-zero masses. And since, as I said, apart from photons, the neutrinos are the second most ubiquitous particles in the universe, even a very, very, very small mass of the neutrinos is going to actually affect the evolution of the universe. So it becomes interesting from that point of view as well. So there's a whole lot of interesting stuff happening with these very, very exotic particle. But I want to caution you that these experiments take a long time to run because they are very weakly interacting. As you can see, with 600 tons of chlorine, Davis got just one event in 3 days, and with 50,000 tons of ICAL, which we propose to do in INO, we will see only 3 events a day of our new mu atmospheric neutrinos. So these are very, very tough experiments. You need a lot of patience. And also, these neutrino experiments are all done underground to avoid the surface cosmic particles that will otherwise spoil your measurement. So now that we'll know more about neutrinos, let's return to the stellar story. We learned about our sun. Our sun is just an ordinary star. It's in its midlife. It's about halfway through its lifespan. And we know now that there are many stellar nurseries, of which there are two pictures here, N11 on the left, LH95 on the right, which are literally stellar nurseries. Millions and millions of stars are being formed in these clouds. And in each one of them, in each star that is being formed, or each protostar that is being formed, the same principle holds. The thermal outward pressure balances the inward gravitational force. And this is typical for a protostar. About 3/4 of it is hydrogen, and the rest of it is mostly helium. And like we saw in the sun, it had up to, talked about up to beryllium and then boron, which forms part of the PP cycle. There's also a smaller cycle in the sun, which is called the CNO cycle. And that is interesting because how do you get to going beyond 8 boron? Because I talked to you about the story of sun only up to 8 boron. So this is a very special uh, thing. It happens due to Hoyle, who said that there is uh, an excited state of carbon 12, which is almost exactly equal to the energy of the 8 beryllium and the helium that is produced. And if this had not been exactly equal in energy, this beryllium that is produced would have just decayed away. In fact, you can see that the decay time would have been so small. So before it could even interact with the helium and produce carbon, it would have decayed away. And this Hoyle resonant excitation state is something that is absolutely necessary for the story to continue beyond 8 boron. So you remember beryllium and boron, but the beryllium produces carbon, then the carbon, nitrogen, oxygen. The CNO cycle is the next most important cycle in the sun. So you have small amounts of carbon, nitrogen, and oxygen in the sun. And in fact, this nucleosynthesis of carbon, so that you can get beyond boron, which is in all large stars, is actually essentially due to the driving energies due to the Hoyle resonance. So what happens now beyond carbon? As I said, this is the CNO cycle. I don't want to go into details, but I want to go to what happens beyond CNO. So as I said, our sun is just another star. For billions of years, it will be in hydrodynamic equilibrium with the inward and outward forces due to gravity and thermal pressure just being balanced. If the star is less than 8 solar masses, where m sun is the mass of our sun, which is of course the obvious unit to use, it simply cools into a white dwarf, as you can see here. Okay, and that's what our sun will do. So as it goes on, this we are here about 4.5 billion years, and as we go on, it will get larger and larger. It will lose its fuel. It will become a red giant, and then slowly cool away into a white dwarf. If the star is slightly more massive in the beginning, from 20 solar masses, it actually collapses into something called a supernova, and the remnant is a neutron star. So I will tell you the story of that in a little moment. And just to complete, if the star is extremely heavy, it simply collapses into a black hole. So let me get to these mid-range stars or supernova explosions. So this is a typical example of a supernova which shines uh, really brightly in the sky for a short time. And this happens for the following reason. As we know that the hydrogen fusing into helium is what is dominantly happening in the sun. But what happens when the helium is all depleted in the core? Gravity takes over, compresses the star, the temperature increases, because whenever you compress a gas, its temperature increases, and that's enough to ignite the helium itself. So the helium fusion now starts, and it continues, and the star acquires an onion skin pattern, because as each and every one of those elements dies out or is depleted, that inner core compresses, becomes hotter, and in layers you get helium, carbon, neon, oxygen, silicon, and iron. And the final silicon iron core, really, really hot, has a mass which is very famous. It's the 1.4 solar masses, which is the Chandrasekhar limit. And once this silicon burning, which happens in just one day of the entire 1,000 billion years of its life cycle, the entire thermonuclear fusion process comes to an abrupt end. That is because I should have shown you that. I'm sorry I missed it. Uh, the lighter elements fuse because they are exothermic processes. Heavier elements such as uranium and thorium fission because that is the corresponding exothermic process. So if you come to the mid mass region, which is exactly at silicon and iron, they are neither exothermic with respect to fusion nor exothermic with respect to fission, and therefore there is no more spontaneous exothermic process to continue, and therefore the entire fusion process comes to an end. The core starts to contract for the last time. The temperature increases until the kinetic energy around 0.511 MeV, which is the mass of the electron, allows the electron capture. So the electron of the atom in the innermost shell of the atom is captured by the proton in the nucleus and converted into a neutron. And this is how you get a neutron star, because the neutronization of the core occurs. This happens in few milliseconds, and neutrinos are produced only of E type. So the first signal of supernova explosion is these so-called burst, mu E, which lasts only a few milliseconds. And the second, so here is the picture of the stellar collapse. Here is your onion ring, and then there are just lots of pictures. It doesn't matter what they are. And uh, after this collapse, what happens is that the nuclear fusion processes have come to an end. and there is no more. Okay, I know why I showed that picture instead of saying it in words. So the core is now not having any thermonuclear process anymore. So gravity takes over, material is infalling, but at some point the rigid neutron core, because of the Pauli blocking principle, it's not able to compress anymore. The core becomes rigid and it just bounces out into an explosion. So the infalling material and the outfalling bounce meet in a shock wave, which simply explodes the outer mantle of the star out and leaves a little remnant of neutron star behind. So that's what happens. And the 99% of the tremendous energy, which is like 10 to the power of 53 ergs, which is a number you can't even imagine what it means, which is emitted in supernova explosions, is radiated when the explosion happens, because these neutrinos and antineutrinos help to cool the star. No other particle can cool the star because of the huge masses involved, because they just simply stay in that very strong gravitational field of the star, and they cannot leave. So it's only the neutrinos which get radiated away. And in fact, all this theory that we have made, the only the only detection in neutrinos, I should have mentioned that, I got that wrong. The only detection of neutrinos from such supernova happened February 23rd, 1987. That's tomorrow, 34 years ago. There's a hand raised, there's a question. Uh, Sorry. Uh, okay, what CP is, I will come back to maybe. Okay, there's an answer already. There was a hand raised, but I don't see a question. Shall I just proceed? Yeah, there's an answer from Gunta Singh about CP, so I'll just proceed. Okay. Yeah, sorry. Okay. Where was I? Yeah. So the only detection of neutrinos from supernovae, which got the Nobel Prize actually in 2002, uh, was from the supernova 1987A. About 20 neutrinos, such a very large number, were detected by two different experiments in Japan and the US, and a direct mass bound of less than 16 electron volts was placed. Now, actually, cosmology tells you that the sum of the neutrino masses cannot exceed about 1 electron volt. They are really, really light, because we know that the next lightest particle, the electron, is actually 500,000 electron volts. And so you could only verify the gross features of the supernova neutrino spectra. So you know that the whole process that you imagined here on Earth actually is what happens out in the stars. So many supernova exploding every day around in the universe, all of them in this fashion. It's just amazing how much you can learn just sitting in your little corner of the universe. But of course, you could not tell anything about neutrino oscillation because you just had too few events. So now there are bigger and better detectors, and supernova detection is one of the very big things among all the neutrino experiments which are at that energy range. So where is the life coming in? Here is a little very beautiful, I should have at least put a reference for this. I'm sorry, maybe I'll add it later on. So the colors, the blue, of course, is from Big Bang. At the time of the Big Bang, only hydrogen and helium were there. But you can see this golden color due to exploding massive stars and or exploding white dwarfs. And here is your iron. Okay, so all these elements, you can see all these colors beyond carbon, nitrogen, which come from low mass stars, all these objects up to uh, iron, nickel, all these objects, and even beyond, are only coming from supernova explosions. And we know that without the hemoglobin in our blood, whose iron carries the oxygen. I mean, because of COVID, everyone knows all about oxygen saturation in the blood, right? That cannot happen without iron in our hemoglobin. And that source of that iron are all the supernovae in the universe. So yes, we are made of stardust from the energy of the sun, which brings primary source of life to life on Earth, to the iron in other stars. Life on Earth is inextricably tied to our living universe. So that was a overview of the sun, other stars, with a little detour uh, into the India-based Neutrino Observatory. And here are the list of references. I tried to find some references which are suitable for the undergraduate level. I'm sorry, I apologize that I have actually referenced my own paper, but this is written for undergraduates or postgraduates in this Indian journal called Resonance. It's open access. You can take a look at it. A very beautiful account of solar neutrinos by uh, uh, the, the the world expert on John Bakal, who is no more, but his page, a web page at Princeton, has been kept alive. because it contains a lot of reference material, both technical and non-technical. Then the atmospheric neutrinos, a very nice talk yesterday by Roger Wendell. You can look up his talk. The nice little bit more, maybe more like postgraduate level article on supernova neutrinos as a series, part of a series of lectures by Helen Johnston. There's a set of lectures on all different kinds of neutrino physics, which was brought out on the occasion of the 65th birthday of one of our colleagues. It's now quite old, but the reviews are still maybe useful at the undergraduate or postgraduate level. And I hope that you enjoyed this talk. Thank you very much.
Thank you very much for that talk. That was absolutely lovely. I think there's some questions in the Q&A. So if you would like to just go through those and then answer them.
Yeah. Yeah. Okay. Maybe I guess everybody can see these questions, so I don't have to read them out.
Yeah, I think that should be fine.
Okay, fine. So, okay, the first one I am going to skip because I don't quite understand the amount of energy needed to be emitted. Was okay, maybe was a non-integer. The amount of energy is always a non-integer. I mean, I can have continuous amounts of energy, right? You remember that energy E is equal to h nu. So h is a fixed quantity, right? It's a unit of Planck's constant. But the frequency can be anything. Frequency is a continuum domain, right? So anything, the amount of energy can be completely non-integer. That doesn't determine that is not related to the number of neutrinos being formed. I hope I answered that to the satisfaction of the anonymous person. Yeah, I answered this question already about charged leptons. The next question is Gunta Singh. Why do physicists call particle acceleration high energy physics? That goes back to, let me just go back to this. Sorry, I've annotated it. It's a little messy, but oh, sorry. Here. So it's called particle physics is called high energy physics because uh, in order to see smaller and smaller distances, I need to go to higher and higher energies, and that is exactly this equation. Okay, so if I want to probe the nucleus, I would need millions of electron volts. If I want to see the protons or the nucleus itself, but if I want to see within the protons, we know that protons are not point particles. There are quarks and gluons inside. So I need much higher energies to see much smaller distances. So in fact, we know that we need thousands of millions of electron volts, which are called giga electron volts, to see inside. And the accelerator at CERN, the Large Hadron Collider, which saw the Higgs particle, I refuse to call it the God particle. The Higgs particle is actually accelerating protons at 13 trillion electron volts, right? So that's why particle physics, you want to see small particles, you need high energies, okay? That's it. So I hope that answered the question. Sorry, something happened. Some questions started to get deleted. Okay, I think the rest of the questions got deleted. And okay, could there be a fourth generation lepton? Yes, there could be. It's a very nice experiment. The LEP experiment showed that there can be only 3 active neutrinos which are less than half the mass of the Z boson, Z or Z, I don't know what you want to call it, which is the mediator of the weak interaction. There could be a fourth generation, but that will be very, very heavy. Okay. You could also have a sterile neutrino which doesn't have a partner charged lepton, and there's a lot of interest in that as well. Okay, the next is simply a comment. I'll skip that. What is the gamma factor? Okay, the gamma factor is simply this. 2 protons don't like each other, right? So they would not want willingly come together. They're not like electron and proton, which will bind into hydrogen atom. You need to squeeze them, right? So you want to squeeze them by having gravity as a squeezing mechanism. So in the beginning, when the furnaces are not lighted, there's not enough energy to trigger the fusion process. Just the density fluctuation causes the gravity to crunch them together, right? And anything which is crunched gets hotter. But how hot can you make it? Can you really make it so hot that you squeeze them close enough so that they'll start to, all 4 protons come together and trigger off this interaction? No, instead of that, they only need to come close together. This proton has a wave function, the next proton has a wave function, which is an extended object. So they just need to come close together so the wave functions overlap a little. And the moment they overlap a little, you get a non-zero probability for this interaction to occur. And then that starts off the process. And once that fusion process starts off, so much energy is released that that process simply continues. Okay, that factor is actually this, the gamma factor just computes for you, given a certain temperature and given the amount of mass, which is the gravity effect, how much is the probability of overlap. That is the gamma factor. What am I currently working on? I think it was already answered in the introduction. Does the weak hypercharge on opposite spin neutrinos guarantee that the opposite spin without the weak hypercharge is real? No, there is nothing about real. Uh, okay, I have, this is maybe, I don't know, apologies to those who don't know what hypercharge is. Uh, there are two things over here. Hypercharge is determined by, okay, I don't know where to begin. Okay, weak interactions, a charged current weak interactions interact with uh, two particles at a time. For example, you saw this interaction, which is, I think, nice over here. You can see this process. So look at this, nu E goes to E. Okay, let's not look at the bottom one. There's an approximation there. But if you look at nu E going to E, so nu E and E are put in the same vector. Okay, you can call them the lepton vector. And this allows the W particle. So when nu E goes to E minus, this is a W plus boson which gets emitted. And so the W minus boson would do the opposite thing. It would take the E into a nu E, right? So because of this whatever vector form of this weak interaction, okay, the two particles have different charges, but they must be invariant under certain symmetry, which is what is required by the quantum field theory, and that is called the hypercharge. Now, the way to understand it is the hypercharge is adjusted in such, just an adjustment, okay, which satisfies, I'm not sure you can read this. I don't know if you can read this. It says Q is equal to I3 plus Y by 2. I'm sorry for those who can't read this, but I3 is the spin. So let us say that the neutrino has spin half, electron has spin minus half. That's what puts it into a vector doublet. And we know the charge is 0 and minus 1. So that means you will see that it's adjusted so that both have the same Y minus 1. Okay. So that's all. The hypercharge has nothing more to do than that. And since the charge of the antiparticles is opposite, the hypercharge will be opposite. And I guess, where are we? Sorry, I'm trying to find my question again. So the hypercharge is simply an adjustment in the theory, in the theory or the model of weak interactions, to make sure that the charges come out right, while the particles which are kept in the doublet are allowed to interact with the W and transform from one to the other. I hope that that answers the question. The handedness of the neutrino has nothing to do with the hypercharge. The handedness of the neutrino simply says that the left-handed neutrino is what interacts with the W boson, and the right-handed neutrino, if it exists, we don't know whether it exists, will simply not even see the W boson. It doesn't have weak interactions. That's all. Okay. Uh, so I hope that answers that question. Will we have access to your slides? Yeah, sure. I'm sure that you can have access. If you wish, you can write to my email address. I can send it to you, or maybe the organizers will put it up somewhere. Okay.
Yeah, if you send the slides to me later, then I can share them with everyone.
Yeah, sure, great. Yeah, I can, maybe I need to clean it up a little because I've annotated it, but I'll try to take it again and send you a cleaner version. Okay.
Yeah, no worries.
Yeah, sure. Yeah. Much like how electrons and positrons can annihilate, can the neutron and antineutrino? Yeah, of course they will annihilate. Yeah, they can annihilate into anything. They can annihilate into photons. I hope you realize that electrons and positrons can annihilate only into 2 photons because of certain conservation laws. Similarly, neutrino and an antineutrino can annihilate to the photon will be a higher order effect, because photons, you remember, are mediators of charged interactions. Okay, and neutrinos don't have charges, so they will not really like to talk to photons directly, but they will annihilate, say, into electron positron pair, or a muon anti-muon pair, or even a quark anti-quark pair, or a W plus W minus pair. They can annihilate into many things which are again charge conjugates of each other, right? Did you understand? Yeah. So I guess I'm done with all the questions. Oh, sorry, there was one more. Munib Zafar. Apart from QFT, is a strong equivalent level of understanding in general relativity necessary to pursue research in neutrino physics? Well, yeah, at one level, I think just relativistic quantum mechanics is sufficient for neutrino physics. But yes, I mean, it depends on what you want to do research in. If you're looking at neutrino oscillations, if you're looking at direct, models of neutrino masses, then I think you need more group theory and relativistic quantum mechanics, and you don't need general relativity really. But if you want to look at neutrinos in the cosmological context, I assume that you would need some general relativity. So it all depends. There are so many areas of neutrino physics that you can do research in. How do neutrinos and antineutrinos behave differently? Uh, Goldhaber showed, Wu and then Goldhaber showed that, we just talked about it, that we know that fermions, neutrinos are fermions, they're spin half particles like electrons, and they have spin, and they have, it's an internal quantum number, you can think of it as, but it's also a spin, and it can be projected in the SZ direction, right? In the Z direction, you can think of as being the direction of propagation of the neutrino. Since they're nearly massless, they're always traveling at nearly the speed of light. And the neutrinos have a very peculiar property that the spin of the neutrino is always opposite to its direction, and the spin of the antineutrino is always in the direction of its motion. Okay, and this difference is what causes what is called parity violation, which means that a mirror universe is the same as the original universe in electromagnetism, but the mirror universe is not seen in weak interactions. So if I show you a certain process like what is seen on the screen, nu E going to electron, then its mirror image, okay, which will involve not only flipping, it will involve flipping the momentum direction but not the spin, will mean that that process simply doesn't occur. So weak interactions break this left-right symmetry of the universe, so the mirror universe is not the same. And that is one very major way in which neutrinos and antineutrinos behave differently. And the charge conjugation property means that if I take a neutrino to an antineutrino, an electron to a positron, and so on, if I just convert every particle to its antiparticle, the the it's not necessary that that charge conjugated equation or process will occur. In fact, it simply does not occur in weak interactions. You have to simultaneously go to the charge conjugate universe as well as the mirror imaged universe. And the mirror image universe is called the parity symmetric universe. The charge conjugate universe is called the C charge conjugate universe. And the combined process of charge conjugation and parity universe is what is seen in weak interactions. That is called the CP conservation, which is also broken to a small extent in weak interactions, which is what drives the observed, or you think or hope that this is what drives the matter antimatter asymmetry in the neutrino sector and hopefully in the universe. How big do you think a gravity sensitive particle detector would have to be to detect particles based on mass? Uh, I don't think you can detect a particle based on mass, because we know that in the general theory of relativity, energy and mass are equivalent. So you will not know whether you have a mass or an energy, and there's a curvature of the universe. And it's an interesting question, but I don't directly have an answer to it. I think that people have searched with very, very sensitive, not particle detectors, but the other kinds of detectors, to look for deviations from Newton's theory of gravity, 1 by r squared law. I think that's about as far as you can go. I doubt that you will actually detect the particle itself. Okay. Okay. Gunta Singh has many questions. I am glad that he's showing a lot of interest. Does the concept of a quantum number act as a hidden variable according to Einstein's argument against quantum mechanics? This goes completely beyond the purview of this talk, because I need to explain a lot of things. Otherwise, I'm answering the question only to you. Again, this is a shortcoming of online lectures where I really don't know what the audience is like. So if you forgive me, excuse me, I will not answer this question. Okay, it's just really way beyond the content of this talk, because I have to then talk about hidden variables and Einstein's argument about quantum mechanics, which I really don't want to do. I'm sorry. Yeah, so that I think brings us to the end of this list of questions. I hope everybody got something out of these. As I said, it's really, really very hard for me to just talk to my computer. And I hope that those of you out there whom I cannot see enjoyed this or learned something from this. Please feel free to write to me if you have more questions. And if I know the answers, I'll be happy to answer them for you. Thank you very much.
Thank you again so much. This was really, really great. And I think that the level was just right.
Oh, thank you. Thank you.
Yeah. So I think now, if you have other commitments, feel free to leave. Otherwise, I'm just going to hand over to Naira, who's president of Maxwell Society, and she's going to give some more information about the conference, how you can get your certificates and attendance and stuff like that. So
I thank you. I can listen for a while. That's just fine.
All right, awesome. I'm going to just turn off my video and then make Nayara the co-host. So 1 second.
So is my screen sharing at the moment?
It's just black right now, I think.
Now?
Oh, no, here, now I can see it. Cool.
Awesome. Okay, yeah. So as I mentioned before, you can get certificates for attendance. So if you want to do that, you can go onto this link here and put in the password. So just every lecture that we have throughout this week, we'll have a different password that you can put into the Google Forms. So put in your real name that you want your certificate as well. And then we'll just use that to track attendance in case you want certificates. And as was mentioned before, so you can get a bronze certificate for filling in just this form and just watching all the lectures. And then you can get a silver certificate for filling in a mini quiz, which we'll send after these talks. And we'll also send more details about that in an email. So we'll hopefully send that today as well. And then you can get a gold certificate if you write a short reflection about what you've learned. And that's just like 250 words. Or you could make an artistic piece like a drawing or anything creative instead of writing it if you want. So that's just that. So yeah, we definitely recommend people do that if they want to just get certificates to show that they've been to this neutrino particle physics conference. And also do remember that today we have a quiz at 6 p.m. and there will be prizes for that. It's very exciting. There's going to be like Amazon vouchers. So do come along if you want to win that. And I've heard that there's like loads of cool rounds. Like there's one that is guessing the physicist. So if you know your physicists, then come along and see if you can win some Amazon vouchers. And also tomorrow we have Francesca and Tepe talking about experimental neutrino physics and their experiences with like working with neutrino oscillators and stuff. So that's going to be really exciting. So definitely come along to that as well. Okay, so, and if there's any questions, then you can send them to our email that you've been receiving emails from. So I think that's everything now. And we'll send like more details about, the questions, the quizzes later on today. So thanks everyone. Okay, I'm going to end this now.